Our next speaker is Balint Fleischer. Balint is currently Chief Research Officer at Huawei's Central Research Institute, where he's responsible for research and technology planning in the storage area. He's widely recognized as one of the leading computer architects in the technology industry. He was most recently CTO at the startup Parallel Machines, where he developed new architectures for advancing predictive analytics and machine learning. He was previously General Manager and Director of Architecture for Workstation, Storage, and Server Platforms at Intel, where he managed Atom and Xeon server architecture development, including efforts related to 3D crosspoint and rack-scale architecture. Mr. Fleischer holds several patents, has published articles in many trade magazines, and is a frequent participant at major conferences, and is very active in standard groups as well. And he's often quoted in trade and technical press. Please welcome Mr. Fleischer.
Thank you. Okay, let me just find the clicker. Thank you. It's great to. No disrespect. And, it's great to be here, and it's nice to see so many friends in the audience. To change the pace a little bit, I'm going to talk about software. And you could wonder about, when you have a conference focusing on non-volatile memory and related technologies and subsystems, why anybody want to come in and talk about software. There's a little history behind it. I was leading the team at Intel when we architected the 3D crosspoint into the server platform, and I'm not going to talk about 3D crosspoint, and obviously I cannot talk about the work I did at Intel. But I can tell you one of the big questions we've been struggling with is that, so now you have this incredible nirvana when the server has near infinite memory capacity of some attributes, and what do you do with that? And we spent a lot of time looking into applications, killer applications, and the reality is that if you look at the server use cases, push aside virtualization for a second, the operating system, the application, the various data structures like heap and temp data buffers are using up a few gigabytes of memory. So the question is that, what is the rest of the memory used for? And so I'm going to talk about that one today. Let me just see if, okay. So just to go back a little bit of memory lane. So NVM took off, or flash drive SSDs took off about 10 years ago, if I remember correctly. There was a time when people started to build robust enterprise-class drives using SLCs. And again, we did that at Intel also. And initially, those drives were used for applications where I/O starved. So if you look at kind of compute-intensive and I/O-intensive application, we went after the I/O-intensive applications, and went after the applications where the price points for the initial SSDs were acceptable. And those applications were streaming, media streaming, and applications like OLTP. Those are applications where you either cannot really scale the application itself, or you have some other constraints, which requires using a device like SSDs. The moment MLC drives came out and became viable more in enterprise class settings, suddenly a whole slew of applications take off. That's where the hockey stick started around the SSD adoption. And you could see social network search, HPC started to use them. And just to go back very quickly, and not to spend a lot of time on it, it improved it enabled the tablets and smartphones. You couldn't do without NVM, those devices. And it improved the operational characteristics of tablets. The other things SSDs has done, it enabled new use cases and architectures. So the all-flash arrays came about as a result of those designs. They basically initially were inserted into existing SAN storage. And as you know, that people were re-architecting the guts of the architecture to make sure that there's no I/O bottlenecks there. So if you look at the NVM journey, and this is my last historical side, NVM space has become very mature, and there are really great new technologies like 3D coming out, But basically, if you look at from the product perspective, not from the device perspective, what you see is SSDs of different form factors and interfaces, different capacities, different performance, different price points. You see all flash arrays, of different shapes. There are dozens and dozens of solutions in every category, and the companies are competing on price or somewhat performance, but it's a fairly crowded marketplace. So the billion-dollar question is, what comes next? What is the next thing which is going to change the industry or change how flash is used or NVM or SCM is used in the system? So we believe that the change is going to come from applications which are both I/O and compute intensive. And one of the critical applications there is cognitive computing, and I'm going to talk about that one. So there are kind of two aspects of cognitive computing, and initially I'm going to cover the IT view, and later on I'm going to talk about some of the consumer and other type of devices view. So this chart is a very simplistic chart. There's a lot of, if you look at IDC or some of the other research organizations, they put in different kind of models to define platforms. IDC has this really cool 3-platform solution, the third platform definition, okay? And I'm not trying to either replace it or challenge that, okay? I'm not coming in from the platform side. Basically, it's what IT is focusing on. You are selling products to the IT customers, and IT has a set of objectives they want to achieve. So in a golden age, the focus was enterprise automation. So basically, what happened? The company has a lot of business processes, and they were all manual processes. So they installed big mainframes, etc. The next big phase was, which created a big architecture shift, is enabling online transactions. When I mean transactions, I don't necessarily mean financial transactions. Anything you do in the web is a transaction. Whatever you send a Twitter tweet, or you send a message on social network, it's a transaction. They just have different kind of properties. This was a tremendously important point for IT, because IT suddenly could cater to much larger number of customers and sell to customers and actually solicit feedback and get feedback from them, helping the company to design better products, improve their pricing models or the availability models or what have you. And you can see that in that phase, the transactions, in that phase, the applications changed. And you could see that this is the time where big data analytics and machine learning and deep learning started to get introduced into IT operations to do predictive analytics and some other functions. So cognitive computing has a kind of an interesting history. Those of you who have been around for a while now, that in the mid-80s was a big initiative around AI. So there was a lot of activities around artificial intelligence, and people wrote books about it, how computers are going to be as intelligent as humans. I came from Boston. I live in Boston. So in Cambridge, we had a place called the AI LA, when all the startup companies were focusing on doing list-based computers, designing list-based computers. That effort effectively fizzled out and died. Basically, the industry realized that it's extremely hard to do. We don't understand how human brain is working at any level, so the notion of mimicking human brain behavior and create a computer which is act like a human is just not really a practical objective. What happened from that activity? A lot of the sub-research spun out. So one of them is, for example, natural language processing. So natural language processing, we use it all the time, or many of us. If you use Siri, for example, or Cortana or Alexa, those are all the results of the work being done by the early I/O pioneers and refined ever since, okay? So the whole idea is that you are talking to the computer using human, English language, and the computer is respond to you. And today, a lot of the implementations are more search queries, so you can ask for, movie availabilities or movie times, or you can ask for weather, what the weather is going to look like tomorrow, etc. But you can see that these companies are investing a lot of money into making it more intelligent. So you can actually add functions like I want to order, Indian dinner or something like that, and then the computer, the cloud-based application or function or skill, the proper term is, would remember what is your preference of the meals you have ordered, what is the preference of the restaurant, and is going to basically take the order. It gives you the opportunity to change it and take the order. So basically offloading humans, and complementing human is a big function of cognitive computing. So if you look at the applications there, the use cases are different because you are focusing on risk assessment or finding new solutions. You can potentially imagine a situation where instead of using data scientists to build different kind of queries to understand what the sales results are, you can ask the computer, what is the products mix sale last quarter, what sold, what didn't sell. And during the process, basically what happens, you can engage with the computer to discover the root cause and to model and simulate and come up with a possible corrective action. So in order to do that, you have natural language understanding because you have to be able to interact with the computer. And then you have functions like object recognition, probabilistic reasoning, content analytics. And so these are pretty advanced software functions running on top of the system. So this is a summary slide for cognitive computing. And what I try to do here is separate out the functionality supported and a business benefit. So the business benefit, as we discussed earlier, is identifying connections between people and events, why things happened and what transpired, okay? New insight, so for example, you can find out things which you haven't thought about it by having the computer participating in a discovery process in analyzing different kind of scenarios could help you to understand if you do something else, what would happen. So it can create new business models, you can invent new business models for a company. And Uber is a good example for that. Uber is a classic example for a business model, which is built on cognitive computing. Okay. Moving on to use cases. I promised earlier that I'm not going to only talking about enterprise computing, but I want to talk about a whole slew of other use cases. And going from kind of top to the bottom on the left side, at top you have intelligent device vehicles. The prototype is obviously KIT. And so this is the whole idea is that how do you create a vehicle which is either assisted or unassisted driving, and it basically protects you from all the random events happening on the road itself. Smart homes, there's a lot of experimentation going on smart homes. You have seen efforts from Google and Amazon, for example, to being able to, using voice-activated functions in the home, talk to Alexa, and Alexa is going to turn off or on the light. I think smartphone is still looking for a killer application, but there's a lot of interesting playing happening there. Robot drones. Drones are all over. A lot of the drones are remote controlled, and a lot of drones have camera built into them. I have seen last week a demo for a robot drone, which is actually do an online recognition. So you can actually point, to follow that guy, and then that guy, he's a friend of mine, by the way. If he walks around in a building, the drone would follow him, and it can have different type of applications. Let's not elaborate on what those might be. But those are intelligence built into the system, which is based on image recognition, okay? Smart cities, I will come and talk more about some smart cities in a later slide, but the whole idea is that the basic issue is how do you balance quality of life, and for people who live there, and the basic essential functions like traffic congestion. Teaching assistants. So those of you who like Doctor Who, we are not building Dalek, the robot, the killer robot in Doctor Who, okay? But there are some really good examples. Robots are a fairly broad term now, and people are talking about robots all the way from a voice assistant like Siri, which is a personal assistant. You can have a teaching assistant, or you can have, I showed some other categories, service robots, elderly companions. There's a lot of parts in Asia where aging is a problem, and having elderly companion service robots are a very important research area because it can provide some basic supporting functions for the people. Personal assistant bots, those are the telephone-based applications which have similar level of intelligence, but obviously they don't have any kind of physical movements because you are holding in your hand. The smart enterprise are already covered. So we think that this is going to be driven by or enabled by cloud-based cognitive computing. And why is it based on the cloud? Well, in some cases you have local intelligence, but in many cases, one of the things you may want to do is, like in a case of drone, you can imagine that you want to minimize the power consumption in the drone itself. So you want to take the heavy lifting of the computation and move it into the cloud. And in other cases, you may want to sell a robot, and after market, you want to sell new skills to the robot. So the customer can buy and expand the usage or change the usage of the robot, or you may want to repurpose a robot. So there's a lot of value of the cloud-based cognitive computing to enhance the intelligence of the robot itself. One of the big catalysts is going to be 5G. 5G promises to be low latency, high bandwidth, ubiquitous access, and that's going to provide the connectivity to a lot of these devices. So moving on and getting closer to the topic of the Flash Memory Summit. So one of the things we are envisioning is that there are going to be a new generation of PaaS platforms. We call it cognitive PaaS or CPaaS, going to come about. And these are complex software stack, as you could imagine from the previous description, with all the advanced analytic and deep learning functions. These applications tend to be executed as a data flow. You have some sort of sensory input coming in, and you have to evaluate the sensory input. Then you have to decide, what is the meaning of the sensory input, and what is the context which this detection was made, and then what you want to do about it, and then you do an activity or action output. Okay, so they tend to be executed as a data flow. And what's interesting about them that first of all, you have to have fast response time. You set aside autonomous vehicles for a second because obviously you are not going to have a collision detection system based on a cloud, because you have to have local intelligence there, okay? But all the human interactions, you have to have fast response time because you are interacting with humans. You basically are having a dialogue with somebody. There's a certain amount of tolerance, the humans have for waiting until the computer responds to that. And you can imagine a lot of the commands or requests you may pose to a cognitive system has extremely complex computational background behind it. So the system has to be fast and responsive. It has to be scalable. Sometimes, to show you two extreme examples, the enterprise applications tend to be larger monolithic compute problems, but the robot applications tend to be smaller problems, but many of them. And one of the key parts is that this is different from classic analytics because you are looking at not only current data, but you really need to understand the environment which the robot came from, or the context, or the question, for example, you ask from this IT architecture prior to that, because it's a learning process. You are learning from, you have to remember what was the results of the previous query because you are building on top of it. As a result, a lot more data has to be not only stored in a system, but a lot more data has to be made available during the real-time processing phase. So we believe that proximity to a data is key, and I will come back to that point because this is kind of the key point of the presentation with some more details. So the target applications could be enterprise applications, as I mentioned, or a list of the applications we had on the previous slide. But one of the interesting things about having cognitive application running on the platform, just to elaborate on a point I made earlier, is that you have a system which can be expanded. So you are not selling, the customer is not buying a closed box, and a closed box will have a functionality, like a DVD player, okay? You buy basically a product which is extensible, reversible. So we call it software-defined robot, and basically what happens, you can take a robot itself, and you can change the personality of the robot, the function of the robot, and you can change the application. So the same robot can be a hotel concierge one day, or could operate in a retail settings, and help selling some merchandise another day. So this would be the place where you are running cognitive applications. So the dotted area is the CPaaS platform, and I'm showing kind of container drawing here. And above it, you have this application pipeline. I mentioned earlier that these applications are written as a data flow. So you have sensor input coming in on the left, and response coming out of the right, And the application pipelines are written because of the platform implements a lot of the complex functions. The platform function is defined in a way that the person who develops the pipeline, they don't really have to be deep scientists, in neural networks, or natural language processing. Okay, so in this particular example, it's a smart city. The inputs are going to be sensor data. You can identify images. It could be people or cars, accidents or something like that. And you can sense the environmental information, and then you do the necessary computation on it, and you can do, in this particular case, alerting or traffic routing. So if you are connected into an autonomous vehicle, one of the things happening is that the planning is happening in a cloud. Remember, the car can detect potential collision or lane changes, but the car cannot do its own planning because it has no awareness about the traffic conditions of the road between the destination and the, where it goes to. Okay, so there's an interaction happening between the cloud-based functions and the local functions. So there are two key storage elements are critical to this functionality. One of them is the data store, which contains the models. The model is what you are executing. It's kind of the program. Okay. And the working data set is a combination of sensor data and temporary data, which each of the stages generated. And the other data store is a context data store. So the context data store is, the car is operating in a context. It's driving on a road. It's driving in a particular city. So you have to know where the car is, because the weather conditions are specific to that, or you are talking to the computer and there's a context you are talking to it. You are asking for sales figures, okay? So you have to store that information because this is modifying the meaning and the interpretation of the data. So moving deeper into the storage space. So this is showing I'm showing three different data store here because for convenience reason, I omitted the global data store from the previous slide. So on the left, you have the pipeline and sensor data store. And one of the things, to go more into details, has to support two different modes. There's data parallel and model parallel modes. There are different scaling techniques people are using for building this kind of machines. And one of the interesting things about, and I will come back to that point later, is that storage has a lot of baggage. I've been in this space for a while now, and we all know what storage is. Storage is an object store or a block store or file store, or so we have this interpretation of what storage means, and the same thing is true for memory. Okay, and what happened is that when you are building a cognitive system, what you are storing is not information. You are storing relations. So the brain functions like an associative memory. That's why what happens if you are seeing something, it triggers a memory of some other event or some other context, which we have seen that before. Okay, so the brain functions very differently from storage systems. Okay, it's not linear, and in order to implement an associative store, you have to do like a graph database or something like that. Graph database is really interesting because you are storing a data item. This is kind of the emulation people are doing it. You are storing a data item, but in the data item, you also store the relationship of that data item to other data items. So in order to understand the relationship between two items, you have to find the linkages. So you can imagine that these are sequentially execute read, evaluate, read, evaluate, read, evaluate, kind of pointer chasing operations. Okay? So this is what makes it tricky and complicated to implement it. And this is the one which is the performance driver, one of the performance drivers for this kind of storage system. So the two different blocks there in the middle, this is what we call cognitive storage. The historical data store is basically a fairly straightforward object store. There is not a lot of uniqueness there, and usable for other applications also. So if you want to map the two different elements of the cognitive store, basically what happened is that the model's working data really want to live in a main memory. So a lot of, in the industry, there's a lot of activities around in-memory computing, and it's a relatively small market, but there's a lot of people what they do is they're allocating, they realize that there's a large percentage of the server memory is unutilized, and what happened that you can actually carve it out and build a storage, implement a distributed storage on top of it. So in-memory data store is a variation of that one. Context and knowledge and indices can be sitting in NVMe because it's not as performance sensitive and it's fast enough. So why SCM is interesting? This is kind of the billion-dollar question. So SCM is, and I'm going to quote public information. So SCM is almost fast as DRAM, the way it was quoted, and it will have higher capacity versus DRAM per DIMMs, and envisioned to be less expensive than DRAM. And so these are very interesting attributes because what you need for a cognitive system is a large data store, and it has to be inexpensive. In some cases, persistency matters, but not every situation, okay? And SCM seems to be providing that capacity enlargement, for the server itself, okay? And but one of the problems with SCM, not a problem, but the benefit of FCM, that if it truly has a DRAM category latency, then the current solutions, which are highly optimized for flash, this is NVMe, user space I/O, are good for SCM. I hope Amber is not here, but it's good for SCM. But what happened is that it needs to be vastly improved, for good for NAND, but it has to be vastly improved for SCM. SCM needs something lower latency, more scalable, better solutions, if you want to implement it properly. So we are going to propose something here. So what I'm showing on the right is an SCM software stack we've been developing at Huawei. It is similar to the SNIA software stack, but we have done some special implementation there. So one of the points I made earlier that I always had a problem with calling it memory or calling it storage, and we had a lot of debates at Intel about that, okay? And we should come up with a different name because what the value of SCM is not that it's really memory, it's not that you can fetch instructions and execute instructions for that, because the code footprint is not very big, okay? The value of SCM, in my mind, for data-intensive applications is that it's sitting in a low latency part of the system architecture, is connected to potentially to the memory or the CPU chip directly, okay? So you have no latency, PCIe latency associated with it, okay? And what happens is that you can have a fast access, you can have these pointer chasing functions implemented very effectively, and because of the objects you are reading are variable size, byte addressability has a value there, okay? And so it's not memory, I mean, what I'm nervous about is that at the moment we keep calling it memory, then we want to figure out how if the latency is a little bit slower than DRAM, then, maybe it's the end of the world because it impacts the performance of the CPU, and it doesn't. So optimizing for applications, so one of the things we believe that the next change is going to happen in the industry, and I have only 2.5 minutes, is application optimized NVM. And so how do you do that? Because the challenge always in the industry around if you create an abstracted interface or programming model, it's universal and everybody can use it. If you create an application optimized one, then it's very customized, and how do you scale that? How do you build an implementation there? So the proposal we make is that there needs to be a piece of a functional block, we call it a data coprocessor or DCP, and it would have high-speed engines built into that, and high-speed engines are optimized for I/O functions. So the big debate in industry is always about offload and onload. The problem with if you are running all these functions on a CPU, the CPU is busy running processing, and the fact is that the slower, the faster the storage, and the more application you can perform in the CPU itself, and the more overhead proportionally you are going to utilize the CPU for. The CPU is a very expensive property. It has advanced instruction sets. The next generation CPU will have a 512-bit wide floating point unit, and so you don't want to use it for fundamentally integer applications, So there needs to be a very compact, scalable engine which is programmable. So the way you can optimize for applications is that by creating the proper microcode which is specific to application categories. And this is where the software-hardware co-design model is very critical, because how do you create an architecture without creating a completely proprietary solution and implement programmability? Now, just because my friends from Intel are here, I would envision that this DCP function can be moved into the CPU itself. And again, I'm not talking about Intel strategy, but this is for their amusement, okay? And fundamentally, the future architecture would look more and more like a Harvard architecture opposed to a von Neumann architecture, where you have code memory, which is DRAM or DRAM emulated on one set of channels, and you have the data store sitting on other channels, and the memory controller for the data store could be a DCP-like function. So this would be the next generation node architecture. You basically have an application accelerator, a general purpose CPU, and then you have a DCP kind of function and built around the storage class memory. So this is a high-level picture of the cluster, adaptable cluster. We believe that this cluster could be usable for a lot of both compute and data-intensive applications. So it's not really optimized only for cognitive computing, precluding any other usages. And I'm just showing a couple of technologies or products Huawei has been developing around NVMe drives, which could be utilized, and all-flash array. So this is a summary slide, and I'm already in a deficit for the time. But we believe that cognitive computing is a very important major impact next-generation application, and that's going to be the future of a large part of the computing business. And storage class memory is shaping up to be an enabling technology. Thank you. Thank you.